Hi guys, I hope you are doing well. I'm going to talk about sections 13.1, point 2, and point 3 at the same time. So it's about curves, arc length of a curve, and curvature. So let me start first with the curve. You can, for example, take let's say three functions: x of t, y of t, and z of t. Okay, and then you can define a vector function. So let's say r of t, that will be the vector, say x of t, y of t, and z of t. Okay, so this r of t actually it's called a vector called vector function. So for example, let's say xt is equal to 2t, y of t is equal to t squared minus 1, and then zt is equal to tq plus 1. Okay, so we have this r of t, this vector function r of t, so that would be 2t, t squared minus 1, and tq plus 1, right? Where t here is a real number, okay, where t, let's say, is a real number. Okay, so you can try to, let's try to graph or draw the r of t, which is, we said 2t, t squared minus 1, and then tq plus 1, right? So here, again, this is my x, this is my y, and this is like my z, right? So we have three coordinates, x, y, z. X, this is y, this is z. So if you say t is equal to 0, so then r of 0 would be 0, negative 1, and positive 1, right? So basically what you get is the point, let's say 0, negative 1, positive 1. So let's say you get this point here. Okay, and let's say this is 0, negative 1, positive 1, okay? But this point, again, corresponds to the time t equal to 0, okay? So if the time t is equal to 0, you get this point. So that's r of 0. What would be r of 1, for example? R of 1 would be, so if t, so let's say now t is equal to 1, so r of 1 would be equal to 2, 0, and then 2, right? So r of 1 would be, let's say, this point here. So you get 2, 0, 2. So we get, let's say, let's say this point here. This is 2, 0, 2. So this is 2, 0, 2. Okay, and it corresponds to the time t equal to 1. So so the thing is, for each value of t, so this is here, this is t equal to 0, this is t equals to 1. Let's say this is t equal to half. Here, let's say this is t equals to 2. This is t equals to 3, t equal to 4. This is t equal, to 5, etc. This is t equal to negative 1. This is t equal to negative 3 halves, etc. So if you connect these points, of course, if you join these points, you get what we call a curve. So a curve, it's just, it's not, of course, it's kind of twisted line. Not necessarily, it's not a straight line, it's kind of a twisted line. It's one-dimensional. It's one-dimensional space because it depends only on the variable t. So for each, there is only one variable here, which is the variable t, right? And actually this variable t is called we call the variable t the parameter t, okay? Parameter of variable is the same thing. So it's one-dimensional because there is only one variable or one parameter, which is the parameter t. And actually, so the t, we say that the t parameterizes the curve. So this is my curve. C. with parameter t. So you can actually think of a curve. You can think of a curve as the motion of a particle in the space, and each point of the curve represents some time t. Okay, so this is like t equal to 0, this is t equal to 1. So this is like the position of the particle at t equal to 0. This is the position of the particle at t equal to 1, etc., etc., etc. So each point represents or corresponds to to a time t. Okay. So, and this equation here, this vector function here, so this equation here, it's called the 2t, the 2 squared minus 1t cubed plus 1, is called the parametric equation of the curve. This is the parametric equation of the curve of C, of the curve C. Okay, so we have this, we have the curve C. We have the parametric equation of the curve C. Now, what we can do, of course, we can compute the derivative. So now the derivative of R of t. Okay. So let's say R of t is equal to x of t, y of t, z of t. So if the derivative exists, if the derivative of x and y and z exist, then we can compute r prime of t, and so r prime of t would be just x prime of t, y prime of t, and z prime of t. Okay. For example, let's say r of t is t minus 1, t squared plus 1, and t cubed. Then, of course, r prime of t would be just, 1, 2t, and 3t squared. Now, this derivative, this r prime of t, has some geometric interpretation. So what's this, the geometric interpretation of r prime of t? Well, it's actually the r prime of t is the tangent vector. It's a tangent vector to the curve at the point r of t. So so this is, so you have your curve. This is your curve here. This is your curve C. Okay, so you have this point. Let's say this is my r of t here. Okay, so then r prime of t would be a tangent vector to the curve at the point r of t. Okay, so this is r prime of t. Okay, so r prime of t, so r of t, that's my curve. R prime of t, that's the tangent vector, to the curve. So let's call the curve C, to C at the point r of t. Okay. Now, so that's the interpretation of r prime of t, and actually you can, using r prime of t, you can find the equation, the parametric equation of the tangent line to the curve at the point r of t. So here, for example, so we have my curve C, I have my tangent vector. So if you take this line here, which passes through my point r of t, and which is parallel to the vector r prime of t. So this line here, this line here is my tangent line. So this is the tangent line. Okay. So tangent line, it passes at the point r of t, it passes through r of t. So tangent line to C at r of t is the line which passes through r of t, the point r of t, which passes through r of t, and with direction vector r prime of t, right? Because r prime of t is parallel to the tangent line, right? Here you see here, so this is my, of course, this is my r prime of t, so my r prime of t is parallel to the tangent line, okay? So let's do a numerical example here. Example, let's say find the equation of the line, find the equation of the tangent line to the curve r of t. Let's say r of t is equal to t squared minus 1 and t squared plus 1 at the point 0, 0, 1. At the point 0, negative 1, positive 1. Okay. So again, idea here's my curve. Here's my point 0, negative 1, positive 1. Right, and I want to find the equation of the tangent line. So that would be this line here. So tangent line to the curve at this point, right? So remember, guys, to determine the equation of a line, we need a point. So this line here passes through this point, 0, negative 1, positive 1. So this is like my x0, this is like my y0 and z0 in the parametric equation of a line. Now we need a direction vector. So the direction vector, of course, so we need a direction vector. So this is like my point. So now we need direction vector, and actually direction vector is going to be given by the tangent vector. So that would be the tangent vector. This vector here. This one here. And the tangent vector, that will be r prime of t. Okay. But, of course, it's the tangent vector at this point here, at the point 0, negative 1, 1. So the question is, what's t here? What's the value of t? So this point here, the question is, to which value of t correspond this point 0, negative 1, 1. So of course, you see, guys, here, if you replace t by 0, right, so you get 0 minus 1 and then 0 minus 1 and then 0 plus 1. So then you get 0, negative 1, positive 1. So if t is 0, if t is 0, then r of 0, that will be the point 0, negative 1, positive 1. Okay, so this point here, 0, negative 1, positive 1, corresponds to the time t equals to 0. So now let's compute the tangent vector at the point 0, negative 1, positive 1. So that will be r prime. Well, first, what's r prime of t? R prime of t is 1, 2t, 2t, right? So it's 1, 2t, 2t. But then 0, negative 1, positive 1 corresponds to the time t equal to 0, right? So then my tangent vector at 0, negative 1, positive 1 would be r prime of 0. So it's r prime of 0, which is 1, 0, 0. So that's my direction vector. So that would be like my A, B, C in the equation of the parametric equation of the tangent line. So my tangent line, so here's final answer. So tangent line, so you know it's supposed to be x equal to x0 plus ta. y equal to y0 plus tb, and z equal to z0 plus tc. So x0, y0, z0, we said it's 0, -1, +1, so 0, -1, +1, a, b, c, so plus t times 1, a is 1, t times b is 0, right, b is 0, and c is 0. So that will be equal to t, -1, and equal to +1. So that's the parametric equation of my tangent line to the curve C at the point 0, -1, +1. Okay. Last remark here. So that's about the derivative. Now also you can integrate. So if you have the integral, so when you see integral of r prime of t, so it's just you can just integrate the x of t, integrate the y of t, and then integrate the z of t. Okay, so that will be the integral of my vector function. Okay, now let's move to the arc length. Okay, so what's this arc length? Well, you have your curve, right? This is my curve here. This is my curve C. And what you want to do, you want to measure the length of the curve from this point, let's say, to this point here. So I want to measure the length of the curve between these 2 points. Okay, so I want to measure the arc length. That's what we call the arc length. So I want to measure this. So that will be the arc length. So we want to measure. So we're going to find the length of the curve. So that's what I call the arc length. Between 2 points. Okay, so like here, I want to measure the length of the curve between these 2 points. Okay, let's say this is r of A, and this is r of B. Okay, so this corresponds to the time t equal to A. So this is t equal to A here, and here this point corresponds to the time t equal to B. Okay, so I want to measure the length of the curve between these 2 points, and actually we do have a formula for that. So the length, or the arc length, so the arc length L, so here's my L. Okay, so the arc length L would be the integral from A to B of the length of r prime of t dt. Okay. You can check the lecture notes, guys, for the formula, for the proof of this formula. And actually, I mean, this arc length, it's obviously it's not a straight line, right? So you cannot really use. I mean, it's not really clear how we can compute this arc length. But actually, it's just based on the Pythagorean theorem. Okay, but you can check the details of the proof of this formula in the lecture notes. But let's just do a numerical example here. Let's say you have a curve r of t equal to t squared, 9 of t, and 4t to the power 3 halves. Okay, and you want to measure the arc length let's say from r of 1 to r of 4. Oops. From r of 1 to r of 4. Okay. So, so we're gonna apply the formula. So first we need r prime of t. r prime of t would be, of course, 2t, then 9, and then 4 times 3 halves. So that would be 6 to the power half, right? Now I need the length of r prime of t, so it's just the length of a vector, so it's the square root of, 2t squared plus 9 squared plus 6t to the half square. So that would be equal to square root of 4t squared plus 81. 81 plus 36 t. Okay, and this is actually, the thing is, this is a perfect square, so this is actually square root of 2t plus 9 square. Okay, so this is a perfect square, square root of 2t plus 9 square, of course. Square root and the square cancel out, so that will be absolute value of 2t plus 9. Okay, so don't forget the absolute value here. And then, the answer, so L, the arc length from r of 1 to r of 4, so that's from 1 to 4, t from 1 to 4. So we have 2t plus 9. But t here, it's from 1 to 4, right? So then 2t plus 9 is positive. So we don't need actually the absolute value. So it's just, here's just 2t plus 9, because again, t is from 1 to 4. So 2t plus 9 is positive dt. So that's t squared plus 9t from 1 to 4. So just plug the 4 in the and 1 in the integral, and so that's 4 squared, 6t plus 9 times 4, 36 minus 1 minus 9, so that's equal to 52 minus 10, so that's 42. So what I'm saying here is that this length here, the length of the curve between these 2 points, is equal to 42 units. Okay, and it's really nice, right? I mean, again, this line can be, this curve can be very, very twisted, so it's not just like a straight line here. Okay. Okay, guys, so now I'm gonna just so that's the arc length. I'm gonna talk about the parameterization of the with respect to the arc length. So there is the arc length function here. First, before the arc length function, let me just talk about the parameterization. So when I say, again, parameter, it means a variable. Okay, so for example, if you say r of t is cosine of t, let's say sine of t, for example. Let's say here t in the interval 0 to pi. Okay, so it's just a helix here. So it's like something which looks like something like this here. So that would be my curve C here. My curve C, okay? The parameter here, or the variable here, is t, right? But you can decide to change the variable. So for example, I decide to use, instead of t, I want to use the variable s. Let's say use s, which is equal to, let's say t over 2 pi. Okay, I want to change the variable. I want to change the parameter t. I want to use another parameter or another variable. Okay, I mean, you can do that. I mean, there's no problem. All you have to do is just you replace. So for example, here I decide to, I just decide to use s, which is t over 2 pi. So then, of course, t is just 2 pi times s, right? So then I can write r of t in terms of s instead of t. So then that would be r of s equal to, so cosine of t, but t is 2 pi s, right? So it's cosine of 2 pi s. And then same here, sine of t, so it's sine of 2 pi s. because t is equal to 2 pi s. I decide that t is equal to 2 pi s. Okay, and t, that's just 2 pi s. Okay. Okay, so we have this 2 pi s. Of course, here just be careful. Parameter s, so we said t is in the interval from 0 to 2 pi, right? T is in 0 to pi, but then s, so if t is 0, then s, we said s is t over 2 pi, right? So then s is 0 over 2 pi, so s is 0. And if t is 2 pi, then s is, of course, 2 pi over 2 pi, so that'll be equal to 1. So then, s is between 0 and 1. So here for s between 0 and 1. So what I'm saying here, guys, is that you see we have these two different parameterization, r of s and r of t. However, if you try to graph the two curves, they're gonna be the same curve. So this is I know this is my r of t, right? This is my r of t. And now if you graph r of s from 0 to 1, well, it's gonna be the same curve. So there's gonna be this is also r of s. So r of s and r of t, they describe the same curve. Okay, so r of s and r of t describe the same curve. Well, even if we're using two different parameters, right? Or we are using two different variables, s and t, but still r of s and r of t, they are the same, they represent the same, it's the same curve, it's the same thing. Okay, it's just a different parameter, but different variable doesn't mean it's a different different curve. It's actually the same curve. Okay. Now, so as you can see, you can change the parameterization of a curve. Now, what I'm gonna do, we're gonna use different parameterization with respect to the arc length function. So parameterization with respect to the arc length function. So what's this arc length function? Well, so you see, guys, I have my curve. This is my curve here. Let's say here this is r of a, okay, and r of t here. This is r of t. So what we can do here, we can try to, again, we can try just to measure the arc length from r of a to r of t. And that's, so this is my arc length, right? So the arc length function actually gives the length of the curve from r of a to r of t. So that's definition of arc length function. So arc length function s of t. So what's the definition of arc length function? Well, it's the integral from a to t of the integral of r prime of u, let's say du. So this arc length function gives the length of the curve from r of a to r of t. Okay. And here, just a remark, there's one important remark about this arc length function is that s prime of t, if you use a fundamental theorem of calculus, then s prime of t, or s prime of t, is equal to the length of r prime of t. Okay, that's just by the fundamental theorem of calculus. Okay. So anyway, what we can do, guys, is we have this function, this arc length function, right? And sometimes we can be able to solve for t. So we can solve for t. So then t would be a function of s, and then we can change the parameterization of r of t and use the parameter s instead of t. So then we get what we call parameterization with respect to the arc-length function. So that will be r of s, parameterization with respect to the arc-length function. So that will be r of s. So let's do an example. Okay, so let's say you have this curve r of t. So it's, let's say, 2t, 1 minus 3t, 5 plus 9, or 4t instead of 9. Let's say 4 smaller than 9, so 4t with, let's say, t from 0 to 1. So this interval 0, 1, that will be the interval, let's say this is like interval AB. Okay, so A would be 0, okay, and B would be 1. Okay. So let's parameterize the curve with respect to the arc-length function. Okay, so what we can do is, so step 1, so we have to compute s of t, the arc-length function. So s of t, we said the integral, so from a to t, so a we said, we said a is, that's 0 and b is 1. So a here is 0, here it should be t, and then we have the length of r prime of u du. Okay, so what's the length of r prime of u? Well, r prime of r of t first is equal, so we said, 2t, 1 minus 3t, 5 plus 4t, right? That's r of t. So then r prime of t will be equal to 2, -3, and then 4. So what will be the length now? R prime of t, or r, so then this is r prime of t, so then r prime of u, just replace t by u. Well, there's no u here, there's no t here, right? So it's just a constant here, so it's 2, -3, 4. If there is t here, I have, let's say, 3 minus -3t, so here it should be -3u, okay? But there's no t, right? It's just a constant here, so you don't need to replace, so it's just the same thing here. So -3 here, -3, 4 here. So then the length of r prime of u, so it's square root of 2 square plus -3 square plus 4 square. So that'll be equal to 4 plus 9, 13, and 4 plus 9, 13, 13 plus 16, 16. That will be square root of 29, sorry. So then s of t is just integral from 0 to t of square root of 29 du. So that's square root of 29u from 0 to t. So that's square root of 29t. So what I'm saying is that s, which is s of t, is equal to square root of 29t. Okay, so now at step 2 we can solve. Actually, explicitly, it's not always possible. Actually, it's not. Most of the time, it's not possible to solve for t. But here we can do it. So s is square root of 29t. So then t would be square root of s. So it would be s over square root of 29, right? So r of t was 2t, 1 minus 3t, 5 plus 4t. So just replace now t by s. So then R of S, so then R of S, so it'll be, well, so that's 2 times, so you just, replace t by s over square root of 29, so s over square root of 29, 1 minus 3 s over square root of 29, so instead of t you have s over square root of 29, so 5 plus 4 s over square root of 29, okay? And just one thing here, so t, so t here, where is it? So t is, so we said t is the interval in 0, 1, right? So here, so t, if, of course, if t is 0, then s would be square root of 29 times 0, so this is going to be 0. And if t is 1, then s square root of 29, sorry, times 1, that would be square root of 29. Okay, so then s, so here s is, so s is in the interval 0 square root of 29. Okay, so this is the final answer here. So the parameterization with respect to our arc length would be this, with s in the interval 0 square root of 29. So this is parameterization with respect to the arc length. Okay, let me just say one thing, guys. Interesting thing about this parameterization with respect to the arc length. So here I claim, and you can find the proof in the lecture notes, but the length, actually, if you measure the length of r prime of s, is going to be always equal to 1. So it's r prime of s, so the r prime of s is of unit length. So here, for example, so we said, our r of s was equal to, 2s over square root of 2s over square root of 29, right? 1 minus 3s over square root of 29, and then we have 5 plus 4s over square root of 29. So if you do r prime of s, so that's 2 over square root of 29, negative 3 over square root of 29, and then 4 over square root of 29. But then if you compute the length of r prime of s, so that's square root of, so 2 over square root of 29 square plus negative 3 over square root of 29 square plus 4 over square root of 29 square. So that's square root of, so 2 plus 9 plus 16, that's 29 over 29, common denominator. So that's equal square root of 1, so that's equal to 1. So the thing is, the nice thing about this parameterization with respect to arc length is that the tangent vector is of unit length. Okay, that's really nice property.